Okay, guys, so today we're going to talk about non-homogeneous linear systems of ODEs. So what we've talked about so far is we've done a couple of examples. We've talked about why systems of ODEs are important in models for engineering, and we've done a couple of examples where we have solved some systems of ODEs. So now we're going to sort of develop the general theory, and we'll do a couple of examples for a non-homogeneous linear system of ODEs, right? So when I say that, I mean some sort of matrix equation y prime is equal to some coefficient matrix A times y plus some constant vector G, or I shouldn't say constant vector, some non-homogeneous vector G, of course, which is not identically zero, all right? So just for simplicity's sake, we've sort of developed the theory in the previous video where we needed a lot of things to be continuous in order to have the existence and uniqueness of a particular solution. And we're going to assume that we have all of that, all of those continuity requirements, right? So what we're going to do is essentially find the solution in a similar way that we did for the single equation version, right? So to find a particular solution, or a general solution, I should say, for a non-homogeneous ODE, that's going to be comprised of the solution for the homogeneous part, and of course the particular solution. All right, so in that sense, it's very much the same as for a single ODE, right? So the first thing that we're going to talk about is the method of undetermined coefficients for a system of ODEs, right? So this is a good method, just as for the single ODE case. This is a great method if your coefficient matrix A are just constants, as are the components of your G vector, right? So of course, in this example, you can see that we're about to do that A is all constants. All right. And then here we have that G is a constant times the power of E. So times E term. Okay. So, and again, this will sort of be similar to what we did before when we had sort of the non-homogeneous things as before, and we looked at that table and we chose our particular solution and found what the coefficients are. So this will be sort of similar to that. All right, so the current example at hand is that we want to find a general solution of this system of ODEs where we have our coefficient matrix A is -3, 1, 1, -3, and we want to find the y vector such that this is true. All right, so of course, just as in the single ODE case, we first want to find the homogeneous solution. So we're going to assume that our G is 0, and we want to solve y prime is equal to A times y. All right, so as we saw before, this just boils down to finding the eigenvalues and eigenvectors for this matrix. Okay, so if we do that, we're taking our coefficient matrix A and we're subtracting lambdas on the diagonal. All right, so then we get -3 minus lambda on the diagonal. So we multiply those together and subtract 1. And then we find that we'll get a lambda squared plus 6 lambda plus 8, which of course can factor nicely. And that will give us that lambda 1 is -2, lambda 2 is -4. Now, if we find the corresponding eigenvectors, we can find fairly quickly that V1 will be 1, 1, and then V2 will be 1, -1. So of course, what does the general solution look like? Well, it looks like throw constants in front of each of these vectors and multiply them by e to their respective eigenvalues. And we get this for our homogeneous version, right? Now, we have a little bit of a problem here because for the particular solution case, so this is sort of the start of the finding the particular solution. right? And what we would sort of do before is we would look at our G term, right? So our G, I believe was, I think it's -6 and 2. Yeah. So we have G is -6 and 2 times the e to the -2t. Of course, which is a problem because normally we would assume that our G is just a constant times e to the -2, but that's part of our solution, right? So of course we need to use the modification rule. All right. Now for systems, it works a little bit different. We're going to have an arbitrary coefficient vector u times our t to the e to t times e to the -2t, which is sort of what we would get from before with the modification rule. But we also need to add it to the original term. If you don't have this, it won't work, and you can go through and verify that would not work. But in the system version, you also need this. Also need this term. Okay, so now if we take the derivative of both sides of this equation here, well, we'll get y prime of p, yp prime, right? And then we have to do some product rule, and we'll find that we get that y prime is equal to this once we substitute our au in for in for our different equations here, right? So now we can equate our coefficients, right? And this is going to allow us to say that -2u is equal to au, right? Which tells us that u is an eigenvector of a that corresponds to -2. And we found that earlier, we found that eigenvector was 1, 1, but we can, of course, multiply that by any constant. So we're going to assume that constant is a. Now, if we equate, let's see, so this was equating the t coefficients, I believe, right? Yeah. Now, this is the non-t coefficients. And we have that u minus 2v is equal to av plus g, right, which is -6, 2. And then we find that by plugging in our u, we get aa minus 2v1, 2v2 is equal to our coefficient matrix a times v plus -6, 2. And that allows us to arrive at this system of equations here. Now, since these first two left-hand sides are opposite, we can add the two equations right away, and you can find fairly quickly that a has to be -2. Right? Now, the problem is since you have 3 unknowns and only 2 equations, you're only going to get a relationship between v1 and v2. Right? So you can find that v1 is k, and then v2 is whatever v1 is plus 4. All right? So you get that v is this vector here. All right, but we might as well make it easier on ourselves. Let's choose k to be 0, and then we get that our v vector would then be 0, 4. Right? So now this is going to give us, this part here is our homogeneous version of the solution. And then these two terms here give us the particular version, right? So this was like u times t e to the -2t, and this was v times e to the -2t. All right, which we of course went through and we found. All right, now just be careful. If you were to use different values of k, you would get different values for v, although they would still be valid answers. That's totally fine. All right, but just note that if you choose k differently, you will get, of course, different v values. Okay, so that's that example. And now we're going to look at the method of variation of parameters and how that is different for a system of ODEs, right? So of course, the method of variation of parameters is a little bit more difficult than undetermined coefficients, but this allows us to solve more general systems, right? Because before we had that G was a constant, or a power of E or a quadratic or something like that. But here we're assuming a general G of T. And now your A is no longer a coefficient matrix, but it is dependent on T, potentially. All right, but we're actually going to solve the previous equation that we did just to sort of compare the two answers and see how the theory relates to one another, right? So we're looking at the same system of ODEs as we did before, all right? So of course, a basis of solutions for the homogeneous system, right, which we saw before, is given by e to the negative 2t and e to the negative 4t in the y1 component. And in the y2 component, we have e to the negative 2t and minus e to the negative 4t. Right? So a general solution for the homogeneous system is, take your coefficients, which are these general functions, and multiply them by your constant vector C1, C2, and we can represent it in this way, this y of t times our constant vector C. Right? Now, just as a reminder, this matrix here with our basis of solutions is our fundamental matrix. All right, so just recall that fact. Now what we're going to do is we're going to replace the constant vector C with a variable vector u of t, just sort of as we did in the single ODE case, and we're going to use that to find a particular solution. All right, so now of course if we substitute this in to our original ODE, right, if you take yp prime, you can find that by the product rule. So that's like y prime times u plus yu prime. And that's what you're seeing here, right? And that equals a times y of u, again, just making that direct substitution, plus g, right? And again, just remember, since we're assuming that y1 and y2 are solutions to the homogeneous system, right? We know that y1 prime is a y1 and y2 prime is a y2, which in sort of the component form looks like y prime is equal to a times y. All right, so now if we plug this into this equation here, right, we're now going to get that yu prime is equal to g, right, because what happens there is that you're going to be able to cancel y prime of u and ay times u from both sides, right? They're going to cancel each other out. And you're left with yu prime is equal to g, which if you solve this matrix equation means that we need to find y inverse times g. Okay, so now y inverse, right, which you can find using similar methods as we did in the linear algebra section, right? Or if you're not sure, you can go back and look, or you can find on the internet how to find the inverse of a 2x2 matrix, and you're going to eventually get that your y inverse is 1/2 times e to the 2t, e to the 2t, and then e to the 4t, negative e to the 4t. Right? So now if you multiply y inverse times g, we're finding this calculation here, which you can eventually show is -2 and then -4 e to the 2t, right? And that gave us u prime. But we want u, so what do? We just integrate, right? So we're going to integrate our u vector, and that just happens component-wise, right? And you integrate this from 0 to t, which is going to allow us to say that our u vector is -2t and then -2 e to the 2t plus 2. All right, so then we get that y times u, right? So this was our original basis of solutions y, right, for the homogeneous version. And we're multiplying that by our u vector here, right? And this is going to allow us to get our particular solution, which if we multiply this all through, we'll get this here. All right. Now you notice that the second part is already part of the homogeneous version, right? Because we had an e to the negative 4t in our basis of solutions as before, right? So finally, we can write the general solution, which will be y is equal to, of course, the homogeneous part plus the particular part. So of course, our homogeneous part is the same as it was before. It's given by this. And we just slap C1 and C2 in front of each set of solutions. And of course, the particular part, which again, this this 2 negative 2 e to the 4 negative 4t term can just be absorbed into this constant here. But this other part, this negative 2t, still needs to be part of our particular solution, right? And I guess if you really wanted to, you could do the same sort of with this term here and absorb it into that other part. But this is going to give us our general solution here. All right, so that concludes this video on non-homogeneous systems of ODEs. I hope you enjoyed, and I will see you next time.